Did you see that? Oh, sorry. Let me just get everything ready to go here. Sorry. All right. So we're talking about trajectories. Now, if you're an MLG from the 80s like me, you don't need equations to do trajectories, right? We have trajectories in our head from playing so much scorched earth in artillery. But just in case you aren't an MLG from the 80s, let's look at the math. So we're talking about trajectories, and we've already been doing them. We've done drop and shoot, but now we want to do the famous arc, right? We know a trajectory is the path an object takes through space. And here in intro physics, we always talk about the special case near the surface of the Earth. Same as what we just did with drop and shoot, but now we're going to let it go up in the air and see what happens. So let's draw a trajectory as you've seen them probably before. If we have x here and y here, and we have a mass, and we give it an initial velocity up like that, then the trajectory it's going to take is going to be kind of like this, up and then back down, right? And there's a few parameters of trajectories we like to calculate. One is how high did it go? We could call that little h. That's the height, obviously. We could ask about, we would call the hang time, right? How long was it in the air? TH for the hang time. Of course, this is space, but that's the time it was flying through the air. And we could also calculate the range. That's maybe the most important, is R. How far did it go? Where did it land? When you're trying to hit your opponent and you're playing artillery, R is most important. So we're going to calculate these from just our standard kinematics equations. We could really be bold and start like this. You know, we always break things into x and y. I just want to remind you that you can also write it even more general, just as the r vector. And the r vector follows the standard kinematics equations. The initial position is a vector that is just 0, plus v initial t, that has both components in it, where this is v initial, plus 1/2 g vector t squared. You can write it that way. And I'll point that out because in case you're ever doing something where you need to write it this way, you might wonder why I put a plus there when gravity is down, and it kind of depends on how you define gravity. So here I would write it this way. If I'm to define gravity as g is negative 9.8 meters per squared I hat. So the negative can be in the definition of the vector when you're writing things kind of general like that. More likely you would want to write it like this. You would want to say r is, and let's solve the x motion. So in this case, there is an initial horizontal velocity, and the two things that you need to know going into a trajectory are the magnitude and angle of the initial velocity. You need the full vector. So you've got the theta, the angle, and the initial velocity that you shoot with. That's the initial thing in the artillery game. So the initial x component is just the cosine, right? So it's going to be vi cosine theta t. There's no initial x position, and there's no x acceleration. So that's the entire I hat component. And then in y, starting at the origin, 0, it has an initial y velocity, which is vi sine theta t plus, and it has gravity, plus 1/2 gt squared. And the normal thing to do actually now is to change this positive to a negative, because we're now dealing with just the scalar value of g, 9.8 meters per second squared. So we would call this minus 1/2 gt squared, and that's the j hat component. So this is the position vector version of a trajectory, and now we're going to use it to derive the hang time, the range, and the height. Okay, let's calculate those three components. The first that we'll do is hang time. How long was the object in the air? To figure that out, you kind of have to talk to the equation and say at what time does y equal 0? Well, to answer that, you just go to the y component of the position and you set it equal to 0. And maybe we'll put a subscript h for hang time. We're finding a specific time when we do this. So that component, the y component, was vi sine theta t, so th, the specific time, minus 1/2 g th squared. When does that happen? At th, it's at 0. So now we just solve this for th. So you'd probably factor it. So th times vi sine theta minus 1/2 g th, right? Because it was squared, so you pulled one out, equals 0. And if we want to solve this for th, well, one solution is if th equals 0. But that's not the hang time. Did it give us an incorrect solution? No. At time equals 0, the y position was 0. That's the beginning of the trajectory. This is the one we care about. When is this term 0? This term is 0 when we solve it for th. Bring the 2 over here. Looks like it's the hang time must be 2 v initial sine theta over g. So there's your first one, hang time. That's how long it's in the air. The faster you shoot it, the longer it'll be in the air. The bigger the angle, the longer it'll be in the air, and then the slower gravity is, the longer it'll be in the air. Let's look at the range. That's the critical one. How far does it go? Well, I'm doing my order on purpose here because how far it will go depends on how long it's in the air. So to calculate the range, how far in x during th, you really just have to say we'll use the symbol r to represent the range. It's just the horizontal velocity, which is constant. There's no acceleration. So the horizontal velocity is, of course, just vi cosine theta times t. But t is the hang time. So times 2 vi sine theta over g. Okay? And you combine those and you get, so the normal way to write it is the 2 vi up here times sine theta cosine theta over g. And I forgot that there's 2 vi squared, sine theta cosine theta over g. Right, there's the range. One thing you can learn from the range is what angle do you want to shoot at to get the maximum range, and from this you can tell it's 45 degrees. If you plot sine cosine, the biggest value is at 45 degrees. If you go to 90, one of them 0. If you go to 180 or 0, one of them 0. So halfway is where it maximizes. And then finally the height, how high did it get? Right, the height is basically y at 1/2 th. Okay? Thy has gone to 0, but since the trajectory is symmetric, you know that it's going to be the maximum right in the middle is the easy way to get there. So all we really have to do is get our y expression and plug in 1/2 th. So vi sine theta 1/2 th minus 1/2 g 1/2 th squared. Right, that's the height. So let's start plugging in. There's a little bit of algebra involved, but there's nothing wrong with that. 1/2 th just takes that 2 away, right? So it's vi sine theta over g. So let's plug in vi sine theta times vi sine theta over g minus 1/2 g. And here we're just going to have this thing squared, vi squared sine theta squared over g squared. Vi squared sine squared theta over g squared. Whew, what a mess. And what do we got left here? Both terms have vi squared sine squared theta in the bottom. Both terms have a g in the bottom because this g cancels that g. So it's really the same term minus 1/2 of itself. Right, so if we want to do the algebra in one step, we would say it is 1/2. Well, let's put the 2 in the denominator. It's vi squared sine squared theta over 2g. There you go. That's how high it's going to go if it's a nice symmetric trajectory. So if you're taking a physics class and you're going to have to take exams, you got to decide, do you want to memorize these or do you want to be able to derive them quickly in an exam? So of course in physics we care about deep understanding. We don't want you to memorize things, we want you to be able to derive them. However, in an exam, if you have a limited time, it's often good to have have equations at your fingertips. And fingertips at your equations is also good. But you want equations at your fingertips so you can get through a problem faster and not have to conceptualize a problem and then stop to rederive the range, right? That would take forever. So these are kind of worth memorizing, and it looks hard to memorize them until you realize that they're almost all the same, right? If you think of them as all in terms of vi sine theta over g, this is like 2 vi sine theta over g. This is vi sine theta over g times 2 vi cosine theta, and this one is just sort of that squared. Right? So they're a little bit similar, not too hard to memorize. You ever go to a grocery store in a college town and see ping pong balls for sale in the aisles and wonder, why ping pong balls? Let me tell you why. College students love to think about and experiment with trajectories, especially uneven trajectories. There's this game called beer pong where you take a ping pong ball and you throw it into a cup. And I think if you get it in, the other person does something, but if you miss, you have to drink a beer. I don't really know the point of that part. The fun part really is thinking about your trajectory and trying to get it in and win the game. So we're going to do a problem sort of about this game called beer pong. All right, let me see. I got to get one in here. I made like 5 in a row when we were setting up. Okay, so here we go. So we're going to solve this problem, beginner's beer pong. You throw a ping pong ball from about half a meter high at 3 meters per second, right? And at 35 degrees to the horizontal, 35 degrees above, and into this 20 centimeter, 0.2 meter high cup. So we want to figure out, for this one, how far away is the cup, if all that happened. So we could think about the trajectory. We know it's going to look something like this into the cup on whatever the 7th try, whatever it was. So this is an uneven trajectory because it starts at one height, ends at another height. I usually tell you to solve these problems by writing the position in x and y as a function of time and just solving it. And in this case, because it's uneven, that will actually lead to a polynomial you'll have to solve. You'll have to find the roots of a polynomial. So actually, for these kinds of problems, it's better to not do that. For these, it's actually better to find the apex here and think of it as 2 problems. One is half of a uniform trajectory to go up, and then another uniform half trajectory to go down. And to just think of it as 2 problems, 1 and 2. And then whatever you're asked usually is easier to break it into 2 parts this way. So that's how we're going to solve this problem. All right. So start, as you typically would with these, you want to break your v initial into components, right? So we want to say vy initial is the 3 meters per second times, let's see, the y will be the sine component. So 3 sine of 35 meters per second, which is 1.72 meters per second. All right. And then we need the x. The x initial is 3 times the cosine of 35, which is, of course, this component, the speed it's going forward, 2.46 meters per second. The horizontal is larger because I didn't throw it at that big of an angle, 35 degrees. So now, to solve this, really, you get the idea. What we know is we know the x component stays constant. We just need to know how long it's in the air. Right? How long does it go up, and then how long does it come down? So let's see. So the hang time in 2 parts. And in this case, we're not even going to use the range or the projectile formulas. We're really just going to calculate it. So this part, T1, T1 is simply this velocity, this vertical velocity, 1.72, being reduced to 0 by gravity. So it's 1.72 over 9.8. So it took it about 0.176 seconds to go up. 3 meters per second might have been a little bit of an exaggerated throwing speed for beer pong. So now we need the time for the second part of the trajectory. So we look at that, and it starts actually at a height we don't know yet. It starts up here. So let's figure out how high it got for the second part. That would be, the quickest would be v final squared equals v initial squared plus 2ad, because we're accelerating for a distance that we want. So final is 0. Right? The final velocity squared is 0 in the y direction. The initial velocity is 1.72 plus 2, and the a is 9.8, and then that's the d we're looking for, and it's minus because it's down. Right? So then we'll get d, how high it got above that, and if you work that out, you get d equals 0.151. So now what you know is that the ball has to fall from a height of 0.5 plus 0.151. Fall straight down. How long does it take? Then that would be, let's see, the final position is 0, is the initial position, which is 0.5 plus 0.151, which is 0.651, plus v naught t, which is 0. There's no initial velocity when you're just sitting here falling down, minus 1/2 gt squared, minus 1/2 9.8, and this is t2 squared. Okay, so we bring this over here in the 2, and you divide by the 9.8, and you take the square root, blah, 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 and you get T2, if you work all that out, is 0.3034 seconds. T2 is 0.3034 seconds. So the time for the whole thing, T1, T2, we could call that the hang time. We've basically solved for the hang time for this uneven trajectory. And it's just the sum of those two, 0.176 and 0.3, and it's about 0.479. But we weren't asked for the hang time. We were asked for how far? The range, in this case, the range for an uneven trajectory. So to get that, we just have to figure out r is simply d equals vt, right? So it's how v, the x velocity, 2.46, in the x direction, 2.46 meters per second for 0.479 seconds. And then you get how far away was the cup? 1.18 meters. 1.18 meters. So about a meter away.